Hello everyone, welcome to my channel. This is my channel for educational enrichment. Hopefully will turn you on to some stuff that you didn't know about. Important stuff, theories of everything, all-encompassing theories, paradigm shifters, anything that I think could really help you live your life and help you with your awakening, things that have helped me. And today is our 422nd video that we've done on the reciprocal system of theory from Dewey B. Larson. And around 1959, Dewey B. Larson proposed his two fundamental postulates about how the universe operated. And then he took those postulates and through a process of deduction arrived at his theoretical universe of what would the universe look like if my postulates were correct. And wrote books comparing his theoretical universe with the measured empirical universe of the legacy scientists. And in particular, in this book that we're looking at today, he's taken on the chemists. This book is called Basic Properties of Matter. And he is, Larson derived equations for many of the different basic properties of matter, such as the interatomic distance, the compressibility, the specific heat, the melting and boiling points, and so on. And then he goes to the scientific tables and compares his results with the results of the legacy scientists. And we are about to start chapter 3 here, which is called Distances and Compounds, Interatomic Distances. Chapter 2 was on just interatomic distances, basically of the elements. Now we're moving into compounds. So this might get even further into the weeds, but we will let Larson speak for himself. But first I'm going to speak a little bit to kind of inform you about Larson's theory, the reciprocal system in general. Larson's reciprocal system is basically posits a universe of motion. The universe is not made out of matter, it's not made out of energy, but it is made out of motion. And in particular, it's made out of a more generalized kind of motion that Larson calls scalar motion. This is a motion with a magnitude but no specific direction, that you might visualize using a balloon that you put dots on with a magic marker. And as you blow up the balloon, all the dots will be moving away from each other, but in no specific direction. And as you suck in the balloon and it contracts, all of the dots will be moving toward each other, but in no specific direction, or really in every direction. Not even just to the dots, but to the locations between the dots. They're all moving away from each other as you blow up the balloon and toward each other as you contract the balloon. So scalar motion doesn't have a direction. Really, well, you could say that it has an outward direction and then an inward direction, but those are the only directions that you can impute to the scalar motion. Now, what you can do is you can arbitrarily say that one of the dots is motionless, and by doing so, assigning a reference point, then you are able to determine some directions and make some measurements. Now, Larson says that that motion there, the expanding balloon, he calls that the progression. And then the contracting balloon is analogous to gravitation. And um, uh, in Larson's universe of motion, um, you have to be able to accept the fact that um, motion can exist without anything moving. There is motion before there is anything moving. And that's, a hurdle that you have to leap over before you can even start to take the reciprocal system seriously. Now, other people in the past have tried to construct a universe of motion. They haven't succeeded. There's some, real smart guys like Descartes and Hobbes have tried this. Many others, but they weren't able to succeed. One, because they didn't recognize this concept of scalar motion. Now, this scalar motion doesn't just apply to balloons. It is, it has been observed by scientists, but it just hasn't been reckoned to be significant. They've kind of shoved it under the rug. All of the distant galaxies that has been observed are moving away from each other. And unless you're willing to say that our galaxy is not participating in that, then our galaxy is also moving away from every other galaxy. So we're participating in this kind of a expanding balloon motion. All of the galaxies are moving away from all of the other galaxies. Now, that finding has actually been used to bolster or even originate the Big Bang theory. But that implies that there is a center point, and everything is moving away from that center point. The expanding balloon is a different situation, and there isn't necessarily a way to tell the difference, mathematically or experientially. But so that is one reason why, the prior philosophers have not been able to construct a universe of matter. Another reason is that they didn't kind of redefine motion the way Larson does. Larson defines motion as the relationship between space and time. Space and time are reciprocals of one another, therefore. Motion is basically a fraction, with space or time as the numerator and time or space as the denominator, with the caveat that space and time both come in multiple dimensions. You can have more than one dimension. He says 3. I think you could say more than 3 even. But they come in, space and time come in multiple dimensions, as does motion. And space, time, and motion also are quantized, meaning that you have a minimum unit of space and a minimum unit of time. And you have to have a full unit before you have anything. And so what that means is that if you have one unit of space in one unit of time, space over time being speed, just think of the bicycle as moving 10 miles per hour, 10 miles of space in 1 hour of time, space over time. Speed is space over time. So if you have 1 unit of space in 1 unit of time, you have what Larson calls unit speed. And this unit speed is, for Larson, is really the background speed of the universe. This is the speed that you have that precedes the thing that's actually moving. This outward motion at unit speed is what Larson calls the progression of the natural reference system. So the universe is always moving outward at unit speed in all directions. That is the empty universe, or Larson calls it the null point, the neutral point, the 0 point, the ether, the origin of this universe. And it turns out that this 1 unit of space in 1 unit of time is also equal to the speed of light. So the speed of light is the background speed of the universe. And it takes other motions in order to kind of nullify that speed and eventually create gravitation. Gravitation can only be created by slowing down that speed several different ways, because if you have a 3-dimensional universe, you have to slow it down in 3 scalar dimensions, 3 dimensions of motion. It requires 3 dimensions of space just to express 1 dimension of motion. Okay, so in order to basically gravitate an atom starts with 2 photons at the center. And these photons are simple harmonic motions or wave-like motions that come as a result of nullifying the outward progression in 1 dimension. And these 2 rotate around each other. And then you take that those photons, and then those have to be rotated in 3 dimensions in order to bring about some gravitation. Now, also because of this discrete unit aspect, this creates 3 separate boundaries. First, you have the speed of light boundary that is dividing between 2 separate sectors of the universe. Half of the universe is moving slower than the speed of light, which he calls the material sector. Half of the universe is moving faster than the speed of light, which he calls the cosmic sector. And these 2 sectors are basically inverses of one another, meaning that you have to invert the roles of space and time as you cross the boundary. So in the material sector, which is the sector that we're accustomed to, we have relationships based on what he calls coordinate time or coordinate space, 3 dimensions of space in a still frame. This is kind of like an abstraction, stopping the universe and seeing, taking a static picture. And so we have X, Y, Z coordinates or Euclidean geometry. Moving through time. Time is a scalar quantity here. Time is always getting farther and farther and farther apart, like on the surface of an expanding balloon, or you could say later and later and later. But if you cross that unit speed boundary and move into the cosmic sector, then you have relationships based on coordinate time, 3 dimensions of time, which is a foreign concept to us, in a still frame, and clock space. Space is always moving farther and farther and farther apart, like on the surface of an expanding balloon. But within both the cosmic sector and the material sector, you also have an inside regions within both. And that has to do with the unit of space in the material sector and the unit of time in the cosmic sector. If you have interactions, say 2 atoms interacting, and the interaction is occurring in less than 1 unit of space, which is 4.56 times 10 to the minus 8 meters, then you don't have space. And if you don't have space, you only have time, because the universe is composed out of motion, which is the relationship between space and time. So it has to be one or the other or both. And so if you don't have space, you only have time. Larson calls this the time region. And once you cross that unit space boundary and you move into the time region, then again, the rules invert. And now the progression is moving everything closer together, and gravitation is moving everything farther apart. And Larson actually determines the interatomic distance by the equilibrium between those two forces, between the progression and gravitation. The progression is constant. It's always outward, or in the time region inward, at the speed of light in all directions. But gravitation is variable based on the inverse square law. And so there is a point at which gravitation equals the progression, and that is where the equilibrium of the interatomic distance is established. And the same is true in the cosmic sector, except with time and space inverted. So you have such things that are called cosmic atoms and cosmic molecules. When they interact in less than 1 unit of time, then you don't have time and you only have space. Larson calls that the space region. And in that space region, the rules again invert once you cross that unit time boundary and you move into the space region. Then the progression is now moving inward in time, and gravitation is moving outward in time. And you can establish equilibrium there where the progression and gravitation are equal. Okay, we'll take some of that background information and see if we can make heads or tails of Larson's discussion of interatomic distances in compounds. Thus far in the discussion of the interatomic distances, we have been dealing with aggregates composed of like atoms. The same general principles apply to aggregates of unlike atoms, but the existence of differences between the components of such systems introduces some new factors that we will now want to examine. The matters to be considered in this chapter have no relevance to direct combinations of electropositive elements, aggregates of which are mixtures of alloys rather than mixtures or alloys rather than chemical compounds. Okay, so that's not what we're talking about. As noted in chapter 18 of my book, Nothing But Motion, which is the first volume of his 3-volume set of, this is the second volume, Basic Properties of Matter. The proportions in which such elements can combine may be determined or limited by geometrical considerations, but aside from such effects, unlike atoms of this kind can combine on the same basis as like atoms. Here the forces are identical in character and concurrent, the type of combination that we have called the positive orientation. The resultant specific electric rotation, according to the principles previously set forth, is T over T squared to the 1/2. I believe that's what it says. No, it is, I believe, T to the first power times T to the second power, the quantity to the 1/2, which is the geometric mean of the two constituents. If the two elements have different magnetic rotations, the resultant is also the geometric mean of the individual rotations, as the magnetic rotations. When he says magnetic rotations, he's referring to two-dimensional rotations. And when he says electric, he's referring to one-dimensional rotations. If the two elements have different magnetic rotations, The resultant is also the geometric mean of the individual rotations, as the magnetic rotations always have positive displacements. And these combine because they have to nullify the progression. And these combine in the same manner as the positive electric displacements. The effective electric and magnetic specific rotations thus derived can then be entered in the applicable force and distance equations from Chapter 1. Combinations of unlike positive atoms may also take place on the basis of the reverse orientation, the alternate type of structure that is available to the elemental aggregates. So here again, he's just like in Chapter 2, he's going over kind of the different so-called bonds, the different bonding patterns of atoms and molecules, like atoms or unlike atoms. And, you know, the scientists are famous for saying that, you know, these are ionic bonds. But ionic bonds actually just make up a small amount of the bonding that's actually occurring. There are many other kinds of bonds that do not fit that pattern. And that is a way to shoot holes in their electronic theory of, like, you know, all of these atoms are bonding because of electric attraction. But most of the bonding that occurs is non-ionic. And so this particular example he's giving is the reverse orientation, the alternate type of structure that is available to the elemental aggregates, where the electric rotations of the components differ. The resultant specific rotation of the two-atom combination will not be the required neutral 5 or 10, but a second pair of atoms inversely oriented to the first results in a 4-atom group that has the necessary rotational balance. As brought out in Volume 1, the simplest type of combination in chemical compounds is based on the normal orientation, in which division 1 electropositive elements are joined with division 4 electronegative elements on the basis of the numerically equal displacements. This is kind of like sodium chloride, NaCl. Sodium has a valence of 1, you know, from its closest noble gas, and chlorine has a valence of 1, negative 1. Sodium has positive 1, and so those combine. Now, but that's an ionic bond, but that doesn't explain most of the bonding that's actually going on, or that doesn't apply to most of the bonding. But he's saying the simplest type of combination is chemical compounds based on the normal orientation. The resultant effective specific magnetic rotation can be calculated in the same manner as in the all-positive structures. But as we saw in our consideration of the interatomic distances of the elements, where an equilibrium is established between positive and negative electric rotations, the resultant is the sum of the two individual values rather than the mean. When this arrangement unites one electropositive atom with each electronegative atom, the resulting structure is usually a simple cube with the atoms of each element occupying alternate corners of the cube. This is called the sodium chloride structure, after the most familiar member of the family of compounds crystallizing in this form. Table 7 gives the interatomic distances of a number of common sodium chloride type crystals. From this tabulation, it can be seen that the special rotational characteristics which certain of the elements possess in the elemental aggregates carry over into their compounds. The second element in each group shows the same preference for rotation on the basis of vibration 2 that we encountered in examining the structures of the elements. Here again, this preference extends to some of the following elements and in such series of compounds as CaO, SCN, TLC. One component keeps the vibration 2 status throughout the series, and the resulting effective specific rotations are 5.5, 7, 8.5, rather than 6, 8, and 10. The elements of the lower groups have inactive force dimensions in the compounds, just as in the elemental structures previously examined. If the active dimensions are not the same in both components, the full rotational force of the more active component is effective in its excess dimensions. The effective rotation in an inactive dimension being unity. For example, the values of log of T for magnetic rotation 3 is 1.099 in 3 dimensions, or 0.7324 in 2 dimensions. If this 2-dimensional rotation is combined with a 3-dimensional magnetic rotation x, the resultant value is log of T, the resultant value of log of T, natural log of T, is 0.7324 x, the quantity to the 1/2 power. The geometric mean of the individual values in 2 dimensions and x in the third. The average value for all 3 dimensions is 0.7324 times 2, the quantity to the 1/3 power. Okay, let's go back and look at how his results are. Now, just to let you know, I'm pretty lost. I'm hanging on by a thread here. I have a general idea of what he's doing, but not a full idea. But again, it's a detective story. If I just keep going, he probably will explain some of my questions. Okay, first element listed here is LiH, lithium hydrogen, and the specific rotations are 3 parentheses 2, 3 parentheses 2, and 3. He calculates the interatomic distance, the intermolecular distance, again, which is in angstroms, as 2.04. Observed is 2.04. Lithium fluoride or fluorine, I don't know, 2.04. Calculated, observed 2.01. Lithium chloride, 2.57. Observed 2.57. Lithium bromide, so I guess he's giving the specific rotations for each one of the atoms. And he eventually calculates that at 2.77, observed 2.75. Now he just has straight lithium. I'm not sure why, but calculates that as 2.96, observed at 3.00. Sodium fluoride, I guess, sodium fluoride, 2.26, observed 2.31. Sodium chloride, 2.77, observed 2.81. Sodium bromide, 2.94, observed 2.98. Sodium iodide, 3.21, observed 3.23. Now we move over to magnesium. Magnesium oxide, 2.15, observed 2.10. Magnesium sulfide, 2.60, observed 2.59. Magnesium selenide, 2.76, observed 2.72. And then we move up to the next row to potassium and calcium and scandium and so on. He's again generally within 1% of the value looks like on all of these calculations. So I believe we will stop here for right now and resume this chapter next time tomorrow. And thanks for tuning in. Now, just keep your head up. I'm lost. You're probably lost. You're probably saying, what's the point? Well, you just have to trudge on, and eventually it'll click. It won't click, but one thing will click. And then that will kind of help give you a little bit of an epiphany, and then another thing will click a little bit later. This is a process, and you just gradually figure out how it works, and it makes sense, as you kind of do the discovery and do the detective work of trying to figure out what exactly he's talking about. And again, I don't criticize him for his writing or being ambiguous. He had a gigantic job that he had to do, and he did the best he could. He was one person with no resources trying to put this together, and he did a great job, but there's still a lot of loose ends that need to be tied up. That's why people need to learn about this, because, like I said, I don't know whether it'll be in my lifetime or not, but eventually everybody is going to have to learn this for every subject. So we might as well start now.